Alright, let's go ahead and dive right on in there. Going from pH to Ka or Kb. First up, what is the Ka of a weak acid, HA, if a 0.75 molar solution has a pH of 3.746? Well, we come on over here to our workspace, and we write those info down so that we don't forget them. Now, let's go ahead and draw out our ice table. HA goes to H plus A minus ICE. We have an initial concentration of the HA is 0.750 molar, and 0 for each of the other two. H plus and A minus are both at 0 concentration initially. As for the equilibrium concentrations, well, we actually already have those, sort of, because we have the pH. And from pH, we can get the concentration of H+. Because 10 to the negative pH is the concentration, so 10 to the negative 3.746 for a concentration of 1.79 times 10 to the negative fourth. Now, let's go ahead and do a quick check. Is this going to be negligible compared to the initial concentrations of HA or H+? And 1.79 times 10 to the negative fourth is kind of right there in the sweet spot. Too small to affect the 0.750, too large to be affected by the 10 to the negative seventh that comes from the autoionization of water. So it's negligible on both fronts. Awesome. We can ignore all that other stuff. And that gives us our equilibrium concentrations, 0.750 molar for HA, 1.79 times 10 to the negative fourth for H+, and 1.79 times 10 to the negative fourth for A minus. So we just got to plug those numbers into our equilibrium expression. Ka is equal to H plus times A minus over HA is 1.79 times 10 to the negative fourth squared divided by 0.75 gives us a Ka of 4.27 times 10 to the negative eighth. Now that isn't necessarily meaningful to you guys, but doesn't really matter. That's the answer. Let's run with it. It's a fairly small Ka. Booyah. Alright, let's move on to the other problem I have set up here. What is the Kb of a weak base, B, if a 0.5 molar solution has a pH of 11.227? Now, this problem is going to be very similar to the previous one. I just got to keep a few things in mind. Let's go ahead and set it up real quick. Okay, 0.5 molar, pH is 11.227. The ice table is over here on the left. B plus water makes BH plus OH minus. And I have water crossed out because pure liquid is not going to show up in the equilibrium expression. We can ignore it. So, our initial concentrations are 0.500, 10 to the negative seventh, and 0. So, what are our equilibrium concentrations? Well, pH is 11.227, but we're not dealing with H plus here. We're dealing with OH minus. So we got to find the pOH. Easy enough. pOH is 14 minus the pH. Gives us a pOH of 2.773 and a hydroxide concentration of 10 to the negative 2.773, or 1.69 times 10 to the negative third. Now we can double check. Is this negligible with respect to our initial concentration? See that I got that backwards, so I'm going to go ahead and fix that. It's 0 BH plus 10 to the negative seventh OH minus. That doesn't really matter. The 10 to the negative seventh is absolutely negligible. It's also negligible with respect to the initial concentration of B. It's a difference of 1/5 of 1%. But I'm going to go ahead and pretend that it's kind of not negligible. Just go ahead and plug that in. So that the equilibrium concentration of B is 0.499. It shows up, it doesn't round out, but it does count as negligible. So 0.499 for equilibrium concentration of B, 1.69 times 10 to the negative third for our equilibrium concentrations of BH plus and OH minus. And when we plug those into our equilibrium expression, we get Kb equals BH plus times OH minus over B is equal to 1.69 times 10 to the negative third squared divided by 0.499 is 5.72 times 10 to the negative sixth. And then, just for comparison, like what would we have gotten if we had left it as 0.500, just assumed it was negligible? It's 5.71 times 10 to the negative sixth. So, yeah, it absolutely was negligible. It showed up, even though it didn't round out. It's negligible. Didn't really make a difference. So we could have just, instead of recording the equilibrium concentration of B as 0.499, we could have left it as 0.500, and it wouldn't really have made a difference. All right, that's enough of those examples. Let's move on. All right, and these examples are coming at it kind of sideways. We have Ka and we have pH. What is the concentration we need to get that pH, given that Ka? So we have a weak acid, Ha. We want a 4.50 pH solution, and Ha has a Ka of 3.88 times 10 to the negative 8th. So we hop on over to our workspace. The first thing we're going to need to figure out is the equilibrium concentration of H+. Straightforward enough. H plus is 10 to the negative pH. So 10 to the negative 4.0 gives us a concentration of 3.2 times 10 to the negative fifth for H+, which of course is also going to be the concentration of A minus. And that is going to give us negligible for our autoionization of water, and it's going to be negligible compared to the concentration of HA. But we'll be able to double check that at the end. So we fill in our ice table. X, 0, and 0 for our initial concentrations, minus a negligible change for HA, plus 3.2 times 10 to the negative fifth, plus 3.2 times 10 to the negative fifth, gives us our equilibrium concentrations of X, 3.2 times 10 to the negative fifth, and 3.2 times 10 to the negative fifth. Those are the numbers we plug into our equilibrium expression here on the right. Ka equals 3.88 times 10 to the negative 8th is equal to H plus times A minus divided by HA is equal to 3.2 times 10 to the negative fifth squared divided by X. Then we just solve for X. Multiply both sides by X, divide both sides by 3.88 times 10 to the negative 8th. X is equal to 3.2 times 10 to the negative fifth squared divided by 3.88 times 10 to the negative 8th. Gives us a concentration of 0.027 molar for our acid. And this is where we can go ahead and double check. Was that assumption correct? Is that change in concentration negligible? Well, 0.027 minus 0.000032. Yeah, that change in concentration doesn't show up even a tiny bit. It washes out completely. It's less than 5%. So that assumption was good. Now let's hop back in to the main slides, and here's our other problem. What concentration of BOH do you need for a 8.745 pH solution if that base has a Kb of 4.750 times 10 to the negative fourth? We jump on over to our workspace. pH is 8.745, Kb is 4.750 times 10 to the negative fourth. We're going to need our equilibrium concentrations, and I gave you pH, but there's no H plus here, so we need to get POH. POH is 14 minus pH, so here it's 5.255. Concentration of OH minus is 10 to the negative POH. 10 to the negative 5.255 is 5.56 times 10 to the negative sixth. Let's go ahead and start assuming that it's negligible and fill in our ice table. BOH goes to B plus OH minus Our equilibrium concentrations are X, 5.56 times 10 to the negative 6th, and I don't really feel comfortable assuming that the autoionization of water is negligible here, because that's 10 to the negative 7th, that's about 5% of 5.56 times 10 to the negative 6th. So 10 to the negative 7th plus 5.56 times 10 to the negative 6th is 5.66 times 10 to the negative 6th. It shows up, and it makes a difference. But let's go ahead and plug all that into our equilibrium expression. Kb is equal to B plus times OH minus divided by BOH is 5.56 times 10 to the negative 6th times 5.66 times 10 to the negative 6th divided by X is equal to 4.750 times 10 to the negative 4th. And we solve for X. X is equal to 5.56 times 10 to the negative 6 times 5.66 times 10 to the negative 6 divided by 4.75 times 10 to the negative 4th is 6.63 times 10 to the negative 8th molar. All right, so far so good, but let's go ahead and check that other assumption of negligibleness. Compare it to 5.56 times 10 to the negative 6. That change in concentration is 100 times larger than the final concentration we came up with. So we cannot assume negligibility. If I gave you this problem on a test, it would be kind of ridiculous. It would be very difficult to solve. But giving it to you on a homework might be more doable, but I don't think I'd do it there either, just because this is kind of nasty. I have to be very careful about how I set up these problems. In any event, that is how you would solve this problem, or at least how you would start solving this particular problem. Let us move on. Now, a question that might come up is an XOH going to be acidic or basic? That is going to depend on X. There are a lot of things that have an OH on them, a hydroxide or an alcohol. Sometimes that is an acidic proton, and sometimes it is a basic hydroxide. And the quick way to tell, the rule of thumb, is that if X is electronegative, you're going to get a strong X-oxygen bond, meaning you're going to have acidic protons. If X is not electronegative, then you're going to get a weak bond between X and oxygen, and thus you're going to get hydroxides, basic hydroxides. So metals tend to produce those basic hydroxides, sodium hydroxide, potassium hydroxide, etc. Nonmetals tend to produce oxyacids, like the ones shown here. Up top we have phosphoric acid, H3PO4, and you see that you have the nonmetal phosphorus bound to all those oxygens, and you break the oxygen-hydrogen bond for each of those. It has 3 acidic protons. Similarly, down and to the right you have H2SO4, and down to the left you have H2CO3. Now you have another trend here, in that the more electronegative that central atom, the stronger the acid is going to be. Because phosphoric acid is a strong acid. Sulfuric acid is a strong acid. Phosphoric acid is a weak acid. And carbonic acid is also a weak acid. And phosphoric acid is stronger than carbonic acid. Now, there are other factors at play between the difference between phosphoric acid, and carbonic acid. But electronegativity is a big difference. Okay. Moving on. We're running up on 15 minutes, so I'm going to go ahead and call it for this lecture. And when we come back, we'll talk more about the strength of acids and bases and the things that can affect that.